Peter Laussen to come up, and he's actually going to do that. He's going to talk about the application. And when Peter had said to me, please, really, really short introduction, so I am going to adhere to that. But just a little bit of information about Dr. Laussen. He's the chief of the Department of Critical Care Medicine at the Hospital for Sick Children, a professor in anesthesia at the University of Toronto. He's really been a leader in actually applying and doing that in the critical care environment and predicting when people are failing treatment, and also predicting when people are going to code. And you know, as someone who's been involved in sort of hacking clinical medicine and actually absorbing in technology and innovation, we know how hard this is. And we know that in healthcare, there's barrier after barrier after barrier. And so, Peter, thank you for your perseverance and actually getting us to apply things. And we're really excited to hear about actually how do we do this and how can we walk and this technology and improve healthcare. Peter.
Thanks. Well, good morning, everybody. It really is a pleasure to be here. This is a tremendous conference. I'm learning a lot, and I just love to see the interaction between scientists and clinicians. This is the way forward. What I want to talk about, though, is where machine learning, artificial intelligence, perhaps fits into our current day state. Now, it is biased by my current practice, which is in critical care, but I think there is a framework that we can think about where we can fit machine learning, artificial intelligence into our activities, and therefore apply them thoughtfully. I do have some disclosures in terms of where I'm working. First of all, I have supported through CIHR, and I have been working in this space for many years. First developed a way to visualize large amounts or large volumes of data into a web-based platform. That license is owned by Boston Children's, and now I work as a scientific advisor for this company, Idiometry, who now has that license. At Sick Kids, we've developed a data architecture platform to handling large amounts of time series data. And I'm also a developer of what's called risky business events. These are risk management conferences in healthcare that we've been running since 2006, all designed around learning from high-risk industries. I'm going to touch on that a little bit later on, because there are lessons to learn here. I'm not a luminary. I'm a pediatric critical care physician with 30 years experience, and primarily my area of specialty is congenital and acquired heart disease. So really subspecialized, but with a huge amount of data streaming from these newborns, infants, and children. I started life in Australia, born and raised, did all my training at medical school, and then fellowships in anesthesia and critical care in Melbourne. In 1992, moved to Boston on sabbatical, and ended up staying there 20 years. And in Boston was where we started to work on trying to develop ways in which we can first visualize the data, because we would look at it but didn't see it, and then how we could then use the data we captured for modeling. In 2012, I came to Toronto to head the intensive care unit here at Sick Kids, and came into this really rich environment that enabled us to really accelerate forward in many ways that I don't think would have occurred in Boston. The ability to collaborate in this university across institutions is enlightening and very much appreciated. Now, I try not to traffic in certitude. That comment came from Leo Celli yesterday as describing physicians. In other words, we are certain all the time of what we do. Well, I work in uncertainty. This is my environment. It's about humans, technology, and data science. Now, this is one area of Sick Kids ICU. We have 2,400 admissions a year into 42 bed spaces. A lot of human interactions here with patients, obviously. The technology is amazing, but the evolution of this area, and particularly subspecialty area of cardiac disease over the last 20 to 30 years is just remarkable. The adaptation of technology, the discovery, the imagination, the utilization, bringing it into the clinical arena was I was pleased to be at the forefront of some of those areas. But it gave us this sense of what is possible and opened our minds. And we're now at that era of data science. We have to have the same imagination, the same creativity, have our minds open to the possibilities because they're huge. Because the future is really going to be quite different. The current state practices that have stood the test of time are going to go away. Dante, you said post-Second World War. I would say post-World War I, if you look at some of the ways in which we practice, such as the way we round in the ICU, for instance. We have distributive healthcare and resources, new environments, new expanded teams. Importantly, we have new generations coming through, people who, in this audience, who are the digital natives, that you are used to using data and seeing it in a different way, and to expect you to come and work in healthcare and put you back in time is a mistake and will set us back. We have to adapt to the new generations and the expectations of those new generations. We have new tools, and in particular have new and massive amounts of data to enable new intelligence. And these are affording new opportunities for collaboration and sharing. And we've already heard the connection between Trillium and Vector as a prime example of that. But these are some of the threats as I see them. First of all, we've got to be cautious of premature, unjustified hype and expectations. Opinions in social media, opinions in the press, we've got to be cautious here. And there are misaligned incentives. The balance between monetization and the democratization of data, we have to find that balance. We have to be cautious about excess control of the data. And I'm going to say lack of imagination by regulatory agencies, societies, internal and external governance who don't see the possibilities, but rather just see the barriers. We've got to change that. At the same time, we don't want to increase the distance between humans and the data, and that's, I think, a real problem. And another area is the ethical framework, where that needs to be developed. It's in its early infancy, I think, in terms of developing these frameworks. It's going to be an iterative process. So first thing we need to do to get machine learning into healthcare is to understand the problem you're trying to solve. And this does take pediatric critical care, but I think it applies across many areas. First of all, there's the advantage of understanding the efficiencies and our resource utilization, well demonstrated in operational aspects that machine learning has an advantage here. We have to understand what are our modifiable risks. In other words, what is our contribution to adverse events or to adverse outcomes? So looking at safety, preventability, quality, the decisions we make. And then we need to look at machine learning as how it's going to make us better, how it's going to enhance our roles. And my role is fundamentally that as a risk manager and a forecaster. When you break it down to what I do, then you can start to see how machine learning may in fact help me. And we have two ways in which we measure performance in critical care. One is our ability to rescue, and we do that really well. We've been following that metric for the last 20 years, our ability to rescue a patient has not been dependent on machine learning. What will be dependent on machine learning is our judgment, our ability to predict what's evolving. Then you have to map the journey of that data, and it follows the patient. And this is the map that we have in our intensive care unit. We have inputs, we know the outputs, we have a layout with various environments and teams, guidelines, protocols, we connect them to monitors, we have the electronic health record, and we see that as the source of truth, which I'm going to put that in italics. And then we tend to do this. We make decision nodes and we bounce around. And the administrators at the hospital will say to me, you guys are practicing variably. Just stop it. You should be able to practice the same way every time. That variability is costing us money. It's delaying, causing adverse events, delaying discharge, et cetera. A small piece of that is true in my environment. To be blinkered by that is a mistake, because what we deal with is biologic variability. And if my team is not appreciating that variability and responding appropriately, and this is where machine learning is going to help us, then they shouldn't be working in that environment. We've got to distinguish between these two important points. The other thing we need to do is to get the right data. So my environment, we have kids connected to a whole lot of monitors that are streaming and data continuously. It's a Niagara Falls of data, in fact. So Niagara Falls, 200,000 cubic feet per second. We're collecting 200,000 bytes per second in our ICU from our 42 beds right now. We have on our website, we document just how much data that looks like, and this is from a week ago, but we were collecting nearly 19,000 data points per second. There's over nearly 2.3 trillion data points in the database. And we've made the decision that we're not going to purge this data. It makes no sense to do that. But that has been the pattern in healthcare. If you don't know what to do with the volume and the veracity and everything else about the data, then we'll keep it for a period of time and get rid of it. We assume we've extracted what we need to know, and that's wrong. So we have made the fundamental decision that the patient owns the data. Therefore, you have to store the data permanently, and it has to be discoverable. When you make that mindset, it overcomes consent barriers, and it also forces you to do something about the structure of that data. And we had to build this data management platform that allows us to compress, decompress, index the files to solve that input-output barrier. We developed this because there's no off-the-shelf product that can handle the variability and the variety of data that we have coming at us. So you have to be creative, but you also have to have the right team. So the team and this is really important, and people in this room should all be part of teams. So this first group here that I've highlighted is within the lab, but that lab is in the heart of the ICU. It's not in another area. There are physicians, nurses, physicians, computer scientists, and people with all sorts of capabilities around capabilities that bring an ability to see the data in a different way, such as a seismologist, PhD in seismology and signal processing, neuroscience, those types of capabilities. We're not constrained by one of us being the leader or one of us being the primary person who is trying to direct. We take direction from people who have different views. Another very important component is our partnerships, and we are really fortunate to be able to partner with Anna Goldenberg and her team. The richness of that collaboration is huge. And this is a very important piece, the human factors component. So we now partner and have done so for the last 5 years with Patricia and her team at Human Era at the university. So we combine a team of taking and analyzing the data with the human factors component, and now you start to understand more about that journey of the patient. And we need funding. This is expensive, but I'm very grateful for all of the support that I've shown here. So where does medicine need ML? Well, I'm not going to point you to specific areas. I want you to think about it, when will ML help us? So ML in these 4 areas that I'll touch on. Let's take the first one. So ML will help us when it is superior to human capabilities. And that's where image recognition comes in. Our retina, our optical pathways are just not mature enough, good enough to pixelate the data, to see what additional information that's contained within an image. Clearly, that's going to have a big impact and is already, and will continue to translate across many areas. The second area where our human capabilities are limited relates to our ability to assemble information. So processing large volumes of disparate, usually structured, often labeled data, such as in the EMR. And that's all about access to knowledge and knowledge transfer. Lots of areas where this type of work has been going, looking at diagnosis and the differences within subpopulations, trying to evaluate risk, looking at the triage of patients, so operational things, what's their risk for readmission, the length of stay, the risk mortality. I actually don't pay much attention to any of those. What are the outcomes of interest for a particular disease, and to compare and benchmark. So there's a lot of administrative aspects about this, but you should apply machine learning in these circumstances because we're just unable to do it ourselves. No arguments. We should apply machine learning when it's going to change our behaviors. And this is our ability to adapt to uncertainty. And this is the work that Patricia Trowbridge and her team have been doing with us. And it's really a grid of uncertainty and adaptation. So we have, when there's low uncertainty, in other words, we're certain what we need to do, you don't need to adapt, that's standard work. That's where we'd like to be for most of the time. Machine learning is not going to help you there. There you've got checklists, CPGs, but too often people try to look at machine learning and think, oh, it's going to help us with standard work. It's a waste of time, don't do it. That's a change of behavior that's doable, known what needs to be done, there's no uncertainty. There are situations, though, where it's illegal normal, there's unnecessary adaptation, and that's really also a matter of training and simulation and CPGs, putting a framework around the way in which people work. We'd like to bring that, obviously, illegal normal to standard work, and that's really a human factors exercise and the way in which we change our behaviors. That's not a machine learning area in my mind. But this is. In areas of uncertainty, we need to adapt. And that is an environment in which I work all the time. And that's where data and artificial intelligence will be very helpful. It will also help us move from this area that we can't be in, which is rigid. In other words, there's lots of uncertainty, but we're not adapting. And we really need to move from rigidity to resilience. Artificial intelligence and machine learning has a real role to play in that. Now, that makes sense, I think. I think it's important to explain that to clinicians as to what we're trying to do with the machine learning and the algorithms that we're going to apply, so that as soon as people understand the value proposition, they're going to adopt them. They're going to be open to them. And if you explain to it where it fits into their workflow and this type of grid, that makes a difference. Machine learning is going to change the way in which we make decisions, but we need to look at it as a decision support system. Augments our decision making and possibly our judgment. So we've heard the black box problem. Physicians, when we've looked at cognitive task analysis, are about sense making. The data that comes to them, needs to make sense to them in the environment in which they're working. And when they look at a machine learning algorithm that they don't understand the inputs, outputs, or the mathematics or how it was derived, then it's seen as a black box. Well, my contention is that we have to deal with our own black box. And when you've got two black boxes looking at each other, we're not going to go anywhere. So we have to get at how we make decisions. And machine learning as a decision support system is extremely important, but let's put it in its context. This is 2018, but it's still relevant. The number one patient safety concern is diagnostic errors. That still continues. I sit on the Serious Safety Event Committee at Sick Kids here. Increasingly, the errors that we talk about are not related to systems, but to the decisions people made. It's a slippery slope, but that's where it's heading. Misdiagnoses, not considered, not appreciated. And decision making is now becoming a performance metric. That makes a lot of sense, I guess, but we've got to understand the context in which those decisions were made. And it's this article in Nature Medicine earlier this year received a fair bit of interest from sick kids about the evaluation and accurate diagnosis of pediatric disease using AI. And this was from China, 1.3 million patients, 101 million data points mined from their electronic health records. The New York Times picked it up, and their first line was, each year millions of Americans walk out of a doctor's office with a misdiagnosis. I don't know where they got that data from, but that's the assumption. What they were able to show was comparable to experienced clinicians. So it elevates the non-expert, doesn't necessarily make the expert any better. And obviously there's a lot of scale to this. There's a lot of areas where we don't have experts, and that's clearly an advantage to have this type of tool, perhaps. But it's also important to understand how we make decisions. We've got the intuitive system one, which is automatic, emotional, with processing and content problems, with gaps, with contamination bias, versus the rational system, which is the slower, more objective, evidence-based system. We operate in the intuitive system about 80 to 90% of the time. And being able to shift from that to a more rational system will come with artificial intelligence and machine learning. It's going to take time to get there. It's going to take time for people to trust that. But I think that's an important area that clinicians will accept that and adopt it when they know how it's making them better. Same when it comes to conditions of uncertainty and signal detection. We heard of the ability about perception and noise. So 75% of our perception looking at signals is about perception, 20% comprehension, 5% is projection. So artificial intelligence and machine learning will boost signals, such as early warning systems. Have no doubt about that. Concern is it could add more noise, so we have to be clear about where this fits in. And then when it comes to making decisions, I talked about the experts and non-experts, and Jeffrey touched on that as well. The difference really is that non-experts are sequential really in their analysis, and they're less flexible to change. The experts understand cues, they recognize patterns, and they're prepared to change their thinking with new information when it arrives. And that's really quite different. Experts and machine learning are the same. And there's no doubt that machine learning will help us recognize patterns, and examples include the risk for an event. So understanding where machine learning fits into our decision-making processes, I think, is very important and will help adoption and implementation because clinicians will see the value. Finally, then, machine learning needs to help us generate new information, and that gets to the biological variability and the individualized aspect of medicine, precision medicine, if you like. And there's lots of inputs into this. Right down the bottom there, I work at the physiologic, physiome, the phenotype, functional aspect, but you can see all these other components that feed into the functional state of that patient. And right now, I'm divorced from those steps above me, and being able to embrace all of that, bring all of that together is going to empower and enrich the decisions that we make for the patients. Being able to bring that together is an engineering problem. There are solutions, and they're going to evolve rapidly. I'm not worried about it. These are engineering problems. They're not barriers that I see in the longer term. So ML in this context will give us new learning, leading to new thinking, and help us embrace uncertainty. It will look for new associations and relationships. I'm going to stay away from any statistical aspects here. We're moving towards compatibility intervals. If you take this article from Nature earlier this year, which is very interesting. But it's an important way for us to think about how we relate the data that's derived from machine learning with our clinical experience as well. Associations, compatibilities. It will also allow us to look at physiologic states and process signals, the addition of additional composite signals that then can be applied to a model, and then potentially models within models. Here's an example, predicting the physiologic state. This is 13 different physiologic signals. It's control theory. We know what the physiologic components are to inadequate oxygen delivery. We take those physiologic components, fit it into the model, and we produce an output of the adequacy of oxygen delivery. This is not based on neural networks. It's based on dynamic Bayesian network, but it's based on known physiologic state first principles. And we use this at the bedside in our ICU all the time. Signal processing, very important in cardiology. This is a patient with atrial fibrillation, and it's now possible to use machine learning to actually detect arrhythmias rather than relying on the human to do so. It's given us a different way to think about data. So now that we have the ability to take through artificial intelligence, develop different ways to look at the data and composite data, we can start to think about things differently. And that's, in my world, it's looking at what's the dose or the exposure to a particular state, how long you've had a low oxygen delivery, how long, and if you look at individual signals, it doesn't get you the answer, but if you take a composite signal and look at it in a different way, it helps. We need to be cautious, though, about the curation of the data. And by that I mean, should we do it at all? What I want to see is a model that's able to handle all of the noise that's coming from the bedside and account for it. We shouldn't be curating the data to the unreal world. This is systolic blood pressure, diastolic blood pressure collected in my unit. We have now over 25 distinct artifacts that we can measure, account for, and consistently see. We've written in the process of writing the algorithms that will allow us to incorporate each of these artifacts within the data. So we instead of trying to curate the data and then model it, we just apply this model into the model we're developing, and we'll be able to account for the artifacts at the time. Much cleaner and easier way in which to do it. I talked about risky business and learning from other high-risk industries. One of the problems with machine learning, particularly in my environment, is that are there any high-risk industries that rely on machine learning when a human life is on the line? I can't think of any right now. And that includes aerospace, includes oil industry, nuclear industry, all of these. They tend to rely on, they like to have something that's provable, a model that's provable. So more likely to use control theory and engineering. But I think over time, as we understand these networks and machine learning, it's going to be more and more that will start to be incorporated within our fields. We have to be open to that and embrace the possibilities. Temper the hype. We are going to boost the signals. We will augment the way we respond to variability. AI, machine learning, is a decision support system. Incorporate it into your workflow. Capture rather than infer our decisions. So I'm not giving you a specific examples where you should study this. I'm trying to give you a framework as to where AI can work, where you can get the data, model it, and work with clinicians within that framework. Because in the end, we really want data that's going to be really reliable, robust, relational, and relevant. We used to talk about the data in time series data in terms of the V's. It's all about volume, veracity, variability, velocity, et cetera. They're all negative connotations. There were reasons why we could not use the data. All of those have been overcome and are being overcome. And that's going to be the story with machine learning in healthcare. And we will get to the R's: reliable, robust, relational, and relevant application of machine learning that will really then change the way in which we practice and really pull us to the future. Thank you for your attention.